feedback by listing its benefits, we're also going to define our basic vocabulary around feedback, which is surprisingly extensive. We're going to be talking about a lot of good things that can come out of feedback in this video, but it's crucial to acknowledge that feedback can cause instability. Anytime you commit to designing feedback into a system, you also need to commit to a thorough stability analysis. An unstable system is usually one that doesn't meet its basic functional requirements, so failing to thoroughly account for instability, especially in weird corner cases where users operate at high temperature or with crazy loads, is a recipe for a lot of wasted effort and broken parts. So with that warning out of the way, there are a lot of reasons to use feedback. The most commonly cited of these is controlling gain reliably. And the op-amp circuit on the right here is configured for non-inverting gain as an example of this gain control. The gain equation for a non-inverting op-amp is 1 plus R2 over 1 as shown here. That gain is independent of any details of the op-amp itself. You'll notice that our differential mode gain doesn't show up in here. It only depends on these resistors R2 and R1. So it doesn't care if our ROs are a little bit different in different transistors, or if VB on wanders around with temperature. That's really cool, because R1 and R2 can be made quite precise as external components, and also ratios of resistors are immune to temperature changes since they both change together. So overall, this configuration gives us a very stable gain against a lot of possible perturbations. We'll take a very close look at the mathematical foundations of that on the next slide. It's also possible for feedback to modulate the input and output resistance of amplifiers. We'll take a close look at that in the next video, but you've actually already seen input modulation in single-stage amplifiers. Emitter followers have some feedback in them that results in a boosted input impedance, and that feedback is also why emitter followers are susceptible to instability with some loads. And finally, we're not going to go over the math of these last two benefits, reducing offsets and improving linearity. However, there's some quick qualitative arguments for each of them. If you have a small offset voltage on an amplifier and negative feedback, then the output is going to move to cancel out the offset, because the output is forced to move to reduce error when you're in a negative feedback configuration. So the op-amp is constrained to drive the inputs together. That's true even if the op-amp has a dead zone at the output. So the output will run past the boundaries of the dead zone in order to ensure that it has enough swing in order to force the input nodes to be equal to one another. And as a result, the dead zones appear much smaller on op-amps because the feedback forces the output signal to live outside of them. As a result, Class B amplifiers are often acceptable as the output stages of op-amps, even though you'd expect them to introduce lots and lots of distortion. Feedback reduces their effect. So let's take a look at this application of gain control. Doing so will give us an opportunity to define lots of useful feedback terms that give us a generic language to talk about feedback control. We can get started by looking at the op-amp and feedback on the left. I've added a few details since the last slide. I've defined the gain of the op-amp itself, which is often called the open loop gain. And I've said it's equal to the variable A. I've also defined an additional variable called F, which is a useful shorthand down here. And that's referred to as the feedback factor, so it tells us how much of our output makes it back to our negative input terminal. And that's just a resistor divider. In our analysis, the feedback factor is always going to be a constant that's smaller than 1, but there are fancy control techniques that let f become a function of s, so just let it be known that we're not covering everything. So we can do a feedback analysis of this op-amp. The negative terminal is related to the output by the factor f, and the difference between the input and the negative terminal makes an error voltage that gets multiplied by A. Um, and that's sort of an exact copy of, or translation of this circuit diagram into a block diagram. Because we can see that V out goes to V minus through F, and then the difference between V minus and V in goes to V out through A. Now, we can analyze this block diagram to find the relationship between V out and V in. I always do that analysis using Black's formula, which says that the closed loop gain, or V out over V in, the output signal over the input signal, is equal to the forward path, A, over 1 plus the loop gain, AF, where forward path is the blocks on the line between V in and V out, and loop gain is the product of all the blocks around the loop. We can factor this expression to make it read as 1 over F times AF over 1 plus AF, which I find to be kind of instructive because this term is very close to 1. So our gain is quite close to 1 over F. And if you were to flip this over, you'd see the sort of gain that we saw on the previous page. It's also possible to notice that because this is close to 1, we can rewrite this term as 1 minus a small error term called the static error. So this term is responsible for our static error, which is this slight deviation from 1 that we see in our closed loop gain. Alright, so that was a lot of terms that we just introduced in this relatively simple line of algebra, and I'm going to go over them again in table form to make sure we understand all of them. The open loop gain is the gain of the op-amp itself. Right now it's a constant A, but the open loop gain often has dynamics inside of it too, and we'll see more on that in the next few videos. And we get it from circuit analysis. The feedback factor is F. In this case it's R2 over R1 plus R2. For us it'll always be a constant that's smaller than 1, but you can play clever tricks by introducing dynamics or gain into it. The closed loop gain is V out over V in for the whole system. I'm being really meticulous about naming this term as closed loop gain because people often confuse it with the commanded gain. So watch out for that sort of ambiguity. We calculate it using Black's formula, which is forward path over 1 plus the loop gain. The loop gain is L, and in this case it's equal to AF, and it's the product of blocks around your feedback loop. The commanded gain is a term that I use and no one else does. This is something that I've introduced to this class because I think it reduces confusion. It's 1 over F. So this is the intended gain for your circuit, or the gain you'd have if your open loop gain was infinite. There's a neat way to solve it that we're going to see in a minute that involves looking at a unity feedback block diagram, or to identify it that involves looking at a unity feedback block diagram. Alright, the static error is this epsilon s, and it asks how far away our closed loop gain is from our static gain. It's the difference between those two values. The static error is the difference between the commanded gain and the closed loop gain. In this case it turns out to be 1 over AF, which you can do by doing a little bit of algebra and approximating this expression. But once we do this kind of neat bit of unity feedback analysis, we'll find that it's always 1 over L plus 1 for proportional feedback. This L plus 1 factor is going to show up over and over again, so I find this to be the easiest way to remember what the static error is. Alright, so I promised you one more way to analyze this that gave us insight into the commanded gain and the static error, and this is it. I like to push the feedback factor here back through the summing junction so that our system consists of a commanded gain block out in front multiplied by a feedback loop that is in unity gain configuration. Unity gain feedback loops always have a gain that's close to 1 because their transfer function is given by L over 1 plus L. So we can express our closed loop gain as 1 over F times L over 1 plus L. You can then rearrange this L over 1 plus L a little bit to show that it's 1 minus 1 over 1 plus L, which is how I get that the static error is always 1 over 1 plus the loop gain. So when you arrange your block diagram like this, you can pick off the commanded gain from the front and identify that your static error is always 1 over 1 plus the loop gain. We're going to be looking at feedback for lots of op-amp systems, and those systems always have 2 terminals. However, you don't need 2 terminals on a circuit to include feedback in it, and we can see that by observing that feedback is actually baked into the operation of an emitter-follower. I included this slide for 2 reasons. First, to show that one-terminal circuits can have feedback in surprising places, and second, to show that the emitter-follower is really easy to model using feedback analysis, which I find elegant. So I've included an emitter-follower on the left of this slide, and I've included our expression for emitter-follower gain below it. It's just there as a helpful reminder. It's easy to draw a small signal model for the emitter-follower, and we did a bunch of circuit analysis on this in order to find the gain expression on the left. As a reminder, that analysis started with finding the total current that flowed into the emitter resistances, RE parallel RO. And by observing that total current was made up of our test current plus the GM generator current. Then finally, we took V out and we added In times R pi, which is equal to this VBE to it, in order to generate V in, and did a bunch of substitution in algebra to find out this AV expression. However, we can also express that calculation using a block diagram. Here, the difference between V in and V out is labeled as VBE. VBE generates 2 currents, one in a GM generator and one in R pi, which is just the same as this expression. Those currents add together and get driven through some resistances to create V out, which is this multiplication. And the difference between V in and V out is used to create VBE, which is sort of a codification of this expression. So this block diagram is an exact representation of the algebra that we did to solve the emitter-follower gain. I think that's really neat, and when I'm trying to analyze a new circuit and I'm getting kind of lost in the algebra, I often try to draw a block diagram in order to simplify out the equations and figure out what's going on. We can use Black's formula on this block diagram to find the closed loop gain, and as usual it's the forward path, this GM plus 1 over R pi times RO parallel RE, divided by 1 plus the loop gain, which is the same as the forward path in this case because we have unity feedback. You can see this expression is identical to the AV we calculated over here, because if we multiplied both top and bottom by R pi, this would turn into a beta, this would turn into a 1, and this would turn into an R pi, giving us the same expression. So this feedback model is accurate in representing the amplifier's operation. That's awesome. It's even more awesome because you can use it to find R in and R out if you think about your feedback analysis carefully, and I'll leave that as an exercise for the reader. So this is cool. It tells us our emitter follower has feedback inside of it, and we can use feedback analysis to understand its operation. Now, one weird thing is if I look at this image, I don't see something in feedback. There's nothing like wrapped from the input to the output. But as we push more current through the base, the GM generator current reduces our base emitter voltage by driving up the output impedance. So that's a type of feedback that reduces the swing across the base emitter junction. That type of feedback is called series feedback, or more specifically series feedback, because this is in series with both the output and the input. And you need to watch out for it. I've seen series feedback on the ground node of high-frequency amplifiers cause instability, so it's good to know that series feedback is a thing that can happen. So in summary, feedback is a powerful design tool that comes with a risk of instability. A very common application of feedback is controlling gain. controlled gains have a steady state error of epsilon ss is about equal to 1 over L, where L is the loop gain. And we also called this a static error with the symbol epsilon s. And you can implement feedback in single-ended circuits like the emitter-follower, which is well described by a feedback model.